The average hourly wage of workers at a fast food restaurant is $6.50 per hour. Assume the wages are normally distributed. Now that's a big clue, right? When we say the wages are normally distributed, chances are we're talking about a situation from chapter 6 where we're talking about the normal distribution. Okay. Assume the wages are normally distributed with a standard deviation of 45 cents. If a worker at this fast food restaurant is selected at random, what is the probability that the worker earns more than $6.75? So if we're talking about, so the average hourly wage is $6.50 per hour. And the standard deviation is 45 cents. We want to know, so what we're asking is the probability that some worker earns more than $6.75. What's that probability? Now, this is a difficult problem to do because if I'm thinking about normally distributed here, for this situation, here's my mean, 6.50. Each standard deviation, I'm adding 45 cents, so this is $6.95. If I add another 45 cents, this is $7.40. Right? If I add one more, that's $7.85. And I can do the same in the other direction by subtracting 45 cents. So $6.05, $5.60, and $5.15. So in general, for the normal distribution, we know that 68% of our values are one standard deviation away from my mean. 68%. If I go 2 standard deviations between 560 and 740, that's 95%. And then 515 to 785, that's 99.7% of my values are there. See, but this problem is asking about $6.75, which is somewhere here, maybe. So $6.75. It's not on one of those indicators that are exactly a standard deviation away, or 2 standard deviations, or 3. It's in between. So in order to do this calculation, I should think about using a standard normal distribution. It's a terrible picture. Where Z is 0, 1 standard deviation, 2, 3, -1, -2, -3. And this value of $6.75 on this normal distribution for this particular situation would lie somewhere close to 1 standard deviation above the mean. Well, I shouldn't put 675 there. But that would be our associated Z value. And the reason why we do this is because we can use our standard normal distribution table, like those previous questions, to determine the area to the left of that value, to determine this area. Which is the probability that the worker earns less than 675, and then subtract that from 1 to find the area that we desire greater than 675. So we want to convert from our value to a Z value, and then use the table to determine the probability of being to the right of that Z value, of earning more than 675. And in those previous examples, I show how to do that. So first, let's convert this X value to Z. So 1, convert to Z-score. And I use my trusty formula, X minus the mean divided by the standard deviation. So the X value, the value that we're considering, is $6.75 minus the mean divided by the standard deviation. So that's 25 cents divided by 45 cents. .555556. For the Z values, I only use 2 places after the decimal, so 0.56. So Z is 0.56. That's the Z value here, 0.56. So what I'm looking for really now is the probability that Z is greater than 0.56. I go to my table. Standard normal distribution table. See, remember, this gives me the area to the left, less than it gives me. So 0.56, 0.56 is 0.7123. So this area here is 0.7123. This area here is 0.7123. But I want the area to the right. I want this area to the right, so if the total area under the curve is 1, I do 1 minus 0.7123, right? Which equals 0.2877. That's the probability. That's the area to the right of 0.56, or the area to the right of $6.75. It's also the probability that Z is greater than 0.56, or that the worker earns more than $6.75. Area, probability, when it comes to the normal distribution, exactly the same. So that's your probability.